Yes, thank you for coming back. So the number is there. All right. Okay, everyone is here. Thank you. Yes, class in session, correct. All right, welcome back. Now, so I just want to inform you in future, you go to your classroom. Can you see your classroom on your screen now? So you shall click at this meet link here. So so this meet link here, every time I will refresh it before I come in, so that I can actually have the button here to record the meeting here. So apparently this is better than calendar. So is that clear, everyone?
Yes.
Coming back?
Yes, Miss.
Right. So let me give you an account on the live session for a while, a short while. Okay, but before that, yes, record meeting. Yes, accept. Right, so I'll mark your attendance. So your attendance here. I've got to wait until everyone is here. All right, so with that, we shall do that later. So can I start now? Okay, so let's go on. Now I want to talk about the lab first, right? Because that day just want to clarify the lab so that when you continue next week, your first session for lab here is clear cut here. So let's start from here. All right. So can you see the screen? It shows your lab menu. Am I right? So can anyone confirm? It's your lab menu screen, right? Correct?
Yes, yes.
All right. Thank you. So let me see if I can take attendance. Okay. All right. Okay. So let's look at your lab menu here. So your lab menu here. So the Monday class on Dr. Nicole's my session there. So we will start with the first experiment, which is crystal structure. So crystal structure here, there will be a video to watch. So upon watching the video, you are supposed to write reports on that here. So as I told you earlier on, this experiment will run for 2 weeks. So if you look at the scheduling from the lab manual, this is the first experiment. It will run for 2 weeks. So please read through the manual and answer the questions based on the manual here. And the question that you answer here, right, results and discussion will contribute to the marks in the marking rubric. So there are a couple of questions. So before you come for Dr. Nicole class or my class or Dr. Moon class, please read through the lecture notes. It is in chapter 2. All right. So this is what you need to be informed of. Okay. So with this in mind here, let me inform you how will I run my practical here. Just to recap. So this practical here, you need to write a format of report. The font size is 12. All this is uploaded in the classroom. I just did it a couple of days ago. So the font size is 12. The type is Time New Roman. Line spacing 1.5. Justify the paragraphing, and upload your report in PDF format to Google Classroom. This is the schedule, as I said to you. The first experiment will run for 2 weeks, and the deadline that I give to you is 5 days upon completion of the experiment here. So you should have ample of time to do a lot of reading and a lot of findings here, because this runs for 2 weeks. All right. So what you have here, basically, I want to inform you. These are the objectives. So recall back when I explained to you with regards to the format to write a report. So objective is critical, because what you write in here will be justifiable in your conclusion. So conclusion and reference are 20 marks, just to recall back the marking rubric. So please make sure you look at this part objectively here. Is that clear? So this is the first experiment. So this is the YouTube video that you're going to watch. The whole first class will present it to you, and mine as well. And so write a report based on the construction of a metallic structure. Here we're talking about mostly metals. We're not talking about ceramics at the moment. It's just pure metal, meaning that we will talk about ferrous and non-ferrous, iron-based metals and non-iron-based metal. All right. So to continue from there, we have lab 2. So lab 2 is talking about microstructure observation. So the microstructure observation is important, because you need to make sure that this structure here goes hand in hand with the strength of the materials. So the strength of the materials here can be changed because of heat treatment. So that's why you see in my experiment, I have a range of 2 heat treatment experiment, and then 2 testing, actually it's not 2, it's 3, because the first one is hardness, second is tensile, the third one is the toughness. Toughness is another kind of testing strength of the material here. So there are 3 testing, mechanical testing, and of course before you can test, you need to look at the structure on the original sample before heat treatment and after heat treatment. And these changes in the strength here comes about from the concept of changes in the crystal structure. So we'll talk about that in lecture 2. Is that clear? Hope you are able to follow. So this is your metallographic preparation, which means we are looking at the microstructure. So these are the objectives. Again, is in the lab manual. Please read through them. This is for experiment 2. So in this experiment here, you will be asked to write a report based on 2 videos. These 2 videos will teach you how to prepare samples for observation of microstructure. Normally, it will be done under my high-end microscope and the normal light microscope that you always have in your biology lab in the school. Those microscope is also applicable. All right. So the samples of a cast iron and a steel microstructure will be provided to you. So what you can do is that there will be of different magnification, how big the microstructure is being magnified. So this will be also used as part of the report writing. All right. So next one here, you can actually have, as I said to you, the 3rd experiment and the 4th is on the mechanical testing. You will test on hardness of the metal. Metal in particular here, a range of ferrous and non-ferrous materials. So we use different testers. The 2 testers that you have here that we always test is what we call Vickers hardness testing, or Vickers hardness tester, and the second one will be Rockwell hardness tester. So these 2 testing method is very common. So if you go into any field of materials, you will see these 2 instruments in the lab here. All right. So now with this in mind here, you are going to watch these 2 videos. So by then we should be able to get more video for you from the actual lab itself here. All right. So I will upload more original video which I will take from the lab as I am allowed to enter the lab here. Right. So experimental data will be provided to you, raw data, actual raw data. All right. So what you do is that you will use this data to calculate the hardness hardness value of Vickers and hardness value of Rockwell here. Again, look at the manual. There are a lot of equations apply, and you can actually convert the scale from one to another scale. All right. So please look at the manual which is in the classroom. I just uploaded it today. right? So the next one is the tensile testing. So tensile testing is about the behavior of materials when it's subjected to force applied vertically. So when you apply a force vertically, which is perpendicular to the area exposed based on the sample dimension. So what you have here, you want to know how elastic will the sample be, right? An example is, for example, you're using a elastic band. So if you pull the elastic band to a certain extent, it will snap and break. So same for all metals, whether they are metals, whether they are composites, whether they are polymer, they will also fracture. All right. So tensile testing, you will have one video to watch here, and the actual video will be also uploaded when I run the experiment. At the same time, if I can, I will show it to you how you set up the sample to be clamped to the tensile tester, and then how do you operate the simulation as well. It is connected to the computer. All right, so it will show you while pulling the sample here, at the same time the force is being detected. The extension of the sample being pulled is also detected by the machine. Right, again here experimental data will be provided to you raw. So this data will be used to calculate, draw graph of stress versus strain, and then from there you can plot and see the behavior or the so-called trend or the pattern of the uh, data that's given to you. All right, so this is the fourth experiment. So the fifth experiment and the sixth experiment, as I said to you earlier on, so I will have these two reports merged together because the basis of these two experiments is on heat treatment. So you will all together need to submit only 5 reports, but you will do 6 experiments because experiment 5 and 6, the report will be merged together. Is that clear? So we are doing heat treatment. So basically, same sample of medium carbon steel, I will subject it to a cooling rate of a different speed, which is what we call quenching. So quenching means cooling in water. All right. So if you heat up the medium carbon steel in the furnace, which is an oven, up to 900 degrees Celsius for half an hour. Upon half an hour, you remove it from the furnace and then you quench it, cool it down in water. So this is called water quenching. So the speed is pretty high, and you will see how the microstructure change with respect to this cooling rate here. So normalizing is what we mean by cooling in air, exposed air. So there are two kinds of air. One is a forced air. It means you use a high speed of air motion. Secondly, is that you just leave the sample as in normal, ordinary room temperature. So it will let it cool down according to normalized range here. So this is what it means by normalizing. It's a technique to change the microstructure of the sample of medium carbon steel. Are you clear? So therefore, you can see this is testing hardness upon applying heat to the sample of the medium carbon steel. So this is one of the mechanical testing. So the experiment 6, you can see the reflection. Again, we test for mechanical strength, but here is toughness. Toughness refers to how tough the sample is upon apply a drastic force onto it here. This is going to cause fracture damage to the surface of the sample. Normally, toughness testing is a non-reversible testing. That means you cannot have back the sample as original shape. Now, compared to hardness testing is a kind of testing here not so drastic. All right, it's not destructive. So if you talk about the impact testing machine or impact testing for testing of toughness, it is a destructive testing because it means that once you test it, the sample will not be able to be used again here. So hardness is slightly different. You can actually repolish the sample surface and test again the same point because you can remove the previous indentation. Is that clear? So what you have here basically, microstructures of this will be provided upon heating up and cooling down in water and in air, forced air, and normal room temperature air. So this structure will be provided to you. So you will need to sketch and illustrate the diagram and label and identify the phases that is available in the microstructure. All right, this will be in the chapters of heat treatment later. All right, so the same in here as you see, lab 6 and 5 will be merged as one report here. So altogether you are handing only 5, and the last experiment you also need to view one of the video. So when I go back to the lab later, all right, is open, then we will actually video the actual machine and show it to you how the operation of that machine works. All right, this is called CHAPI. It's one of the mechanical testing for toughness testing. Another testing of impact for toughness testing is called ISOT. ISOT is for plastic. CHAPI is for metals. All right, experimental data will be provided to you raw as well. All right, any question to ask me? Yes, any question? Because
Sure,
just now,
about the clenching part, right? We
come
go
again.
to
Yes,
where are we gonna do?
sorry, come again. I cannot hear you.
About the clenching part, right? Where are we gonna
Yes,
do? We go
quantum.
to the school to do.
No, because you see, the campus is outbound at the moment for everyone. So the sample will be pre-quenched and the microstructure will be given to you as part of the data.
But
So
then,
you,
like that, everyone having the same stuff, then most of our notes gonna be the same.
most of the structures, the technique for quenching and cooling down of normalizing is the same. So the microstructure will be similar. Yes,
Okay.
the microstructure will be similar because we are using medium carbon steel. You can't have a variation here. But the other three testing, which is the hardness, the tensile, and the so-called impact, the data will not be the same. That means the data is in the numerical value because each one of you note up you're using the same sample, but then sometimes when you test, there is always a subject. It's always subjected to a couple of systematic error here. Okay, so the data will be a range of data there. So each group will have different data. Thank you, Mr. Mo. Very good question. Anything to ask there?
Sure, I still got a question. So it's like each, because we separate to a few sections, right?
That's
So
correct.
each of our section we watch the video or live, like people clenching live, or we watch on YouTube video like that.
That two heat treatment is if I am allowed to enter the lab here, I will do it. I will record it down. But at the moment, it's out of bound there. So that's why the video for quenching and normalizing, they do not have a video for YouTube here. So at the moment, I will provide you a microstructure of the sample upon quenching and normalizing.
Okay.
All right. Thank you for your question. Anything else? Anyone?
Sure. Then what about the like lab three? Can you scroll out to lab three? I have question
Yeah,
about
lab
lab three.
three.
Yeah, lab three there.
Hardness.
Yep, hardness there.
Yes, hardness.
Then about the microscope, right?
Mhm.
You say that they have two methods, right? But then we didn't like hands-on on it, or we didn't hands-on to like learn how to look at the stuff. We just look at the picture. Then like, what if we don't know how to use it in real life?
Yes.
Then these two, these
Yeah.
two
This
techniques.
lab two. Lab two. This lab two. This
Lab two.
this is the microstructure. Yes, lab two. Right. Okay. So you see, it's accurate to say that you do not have actual operation manual to operate the microscope here. So what you have here, that's why the in the lab manual, if you look at the question, one of the question asked is to illustrate the features of a optical microscope here, which is the light microscope, the one that you see in the biology lab in your school here. So from that, you have to know basic fundamental of operation of a light microscope. At the moment, will be onto that focus here. All right. So because everything is quite uncertain at the moment. That's the point that for this experiment here, you'll be provided one the technique to prepare the sample for observation under microscope, and then the microstructure will be provided to you.
Okay.
Thank you.
That's
Any
all the
other
question.
question? Yes.
For the question. Thank you.
Anything
Miss,
else? Yes.
for the
Raymond.
references, can we use the references given in the lab manual?
The lab manual references that book Callister. Yes, talking about that. That book is a very good book. So I would recommend you to have that ebook here. All right, you can get it online. So if you are using that ebook, it's only one, but there are plenty of resources available online. So very good resources online that you can find, but you need to know the key to key in the keywords or what exactly the area that you want to find. So therefore, you have to do a lot of searching and reading up here. Okay, you can certainly use Callister because Callister is one of the main reference texts here. My notes is from Callister, some of it here, not all. All right. So if you have Callister in hand, that would be very good. All right,
Is
but as I told you earlier on, those who are under me for briefing, all right, if you are writing your reference as one reference only, your grading will be what? One or two. Okay, the more references you use, the higher the marks here, but then that portion of marks for references doesn't count entirely from the number of referencing here. So some of your senior will give me like maybe 5 or 6, 7, 8 references here from different sources. It can be a published paper, a conference, a proceeding, or maybe a so-called journal. All right. So doesn't mean that the more references you have, the more marks you get, because the references that you use must be related, must be relevant, must be going hand in hand with what you have explained in your discussion and also in your introduction. Is that clear?
yes, Miss. Thank you.
All right. Any more? Any question? There's a chat here. Someone asked something there. Said no hand, no noise. But yes, Mr. Chan, Huan Eng, what do
No,
you
no,
ask?
nothing. It's just that feeling sad about we don't get to hands-on.
Yes, yes. I understand that. Yeah, I truly understand your feeling here. So are we. Okay, so we hope for the best here. So can I start on to the next part? Can I? May I? All right.
Yes, yes.
Any more question there?
No question.
All right. So look at the manual. Take it one by step here. We understand your circumstances, and also I will consider that as well. All right. Anything we take it as one step at a time here. All right. Is that clear? So let's look at the lecture. Okay, that day the lecture. All right. So thank you to Mr. Soa. Okay. So you reminded me because the day I forgot to click the button there. All right. So today the video is recorded, so it should be fine. So going into Mr. Lee question on the email to upload all the notes there. I'm in the midst of completing the notes here. So you give me some time. I'll try my very best to get the on the classroom when it's ready. All right, Mr. Lee and Mr. Saw. Mr. Lee, are you here? Mr. Saw, all right. Thank you so much for your patience. All right, so let's look at the lecture. So now this paper here is mainly description. Just to tell you, as I told you earlier on, you're going to have 4 questions in the final exam to answer based on these 3 learning outcomes. The fourth one is on the so-called the fourth one is on the practical. So basically, what you have here, this is not in the exam. This is in your report writing, which is going to 5 reports that you have to hand in out of the 6 experiment. Clear, right? So what you have here basically is that you can look into these 3 learning outcome, 1, 2, 3, as you study along the way. All right. So let's make it straight to the point here. So today I'm going to talk about electronic configuration because some of your friends asked me. So now the classification of materials, I just recap here. 1, you have metals. So our focus on metals will be steel. All right, steel is the most important what do you call it product around the world here, and Malaysia is a very good steel producer. All right, so we have a lot of iron in Terengganu, if you are aware of that. So we used to have Kawaja Steel big companies here. All right, so what you have here metallic compound in particular concern we're talking about here is steel. Next one I want to highlight, polymer is one range of the classification of materials. Then we also have ceramic materials, composites, and electronic materials. So today's lecture will not onto this. I want to focus on to talking about electronic configuration. So let's look at electronic configuration. So I understand that you guys may be a bit not able to follow through. So I will repeat myself again here. So what you have here, basically in your Form 5, your teacher will tell you that in order to so-called classify a certain element. So let's say, for example, if I have X, if I have X, right? If I have X as a symbol for an element, so what you need to write is that basically you need to know there is an A and there's a Z. All right. So the A represent atomic mass or mass number. It simply means that this is your proton and neutron. All right. So your Z, which is a Z, is the number of proton. So this is how you represent the chemical symbol for any element. Am I right? So I want you to open up your periodic table. So if you have your periodic table here, so you must have an idea why is it that the periodic table, let me show you the periodic table, arranged in such a way. Let's look at here. Where's the periodic table? Can you see your slides there? Let me search the periodic table. Wait. Okay, this is your periodic table. I put in a periodic table in the lab manual as well. So you must understand why are the elements arranged in such a way. Why are they placed in this position and not other position? Why are they placed in this group and not other group there? So basically, there's a reason for that, and this is based on electron number of electrons. So the number of electrons here that we are packing to the element referring to the number of proton, because what we do at the moment, all atoms of the element, they are neutral, they are not charged. All right, so when they are neutral, that means they have the same number of proton and same number of electron. Are you clear? So when you have same number of proton and number of electron here, so we will use electron to align the element based on the valence electron, which is the outermost electron in the electronic configuration. So before we come to that, so you must know how do you write electronic configuration, right? So in order to write electronic configuration, let's look at the technique. Okay, are you following me? Am I too fast there? Can anyone? No?
You can.
All right, okay, good. All right. So you see here, so the number of electrons is very crucial. It tells me if I have this number of electrons here, I need to know how to arrange them in a way that I can put them into respective group in a periodic table. So this is the first way. The first one is that you must identify what is the principal quantum number required. So we know that n must start from 1, 2, 3, etc. up to infinity. Okay, so this is the principal quantum number. Just like I explained that day, you have condominium, you have many floors, many level. All right, so this is level 1, level 2, level 3. Right, so from the level here, next level we have the subshell. So the subshell, we know that by now, if you have read through, we have the S, we have the P, E, and F. All right, so there are 4 subshell here. So basically, the subshell here will tells me in the reference of the condominium. So on the same floor of every single floor, they will be having 1 unit at each of the corner. and this is repeated. All right, so that means every single level there'll be one, unit 2, unit 3. The same goes to your level of the quantum number. There will be one S orbit subshell, one P subshell, one D subshell, and one F. But in the level of 1 here, the P, D, and F doesn't comes in because it must obey the formula of what? 2n power of 2. This formula must be obeyed because this formula tells me how many electrons are able to fill in when my n equals to 1. All right, it will take in only 2 electrons. When my n equals to 2, it can take in only 4 electrons. And when sorry, not 4, 8. Sorry, 8. All right, when n equals to 3, it can take in 18 electrons. All right, so what you have here, this subshell is very important. It tells me how do I place my electron. So in the subshell here, you will also have smaller level. We call that orbiter. All right, so orbiter is actually space occupied within the atom. So basically, in orbiter that we see here, we label them as boxes. All right, so this is boxes that we label them. So this is the S orbiter, this is the P orbiter, and this is the D orbiter. D orbiter, anyone? How many boxes are there? How many boxes do you think there are?
Five.
Very good. Why 5? Because it's 10, huh? Yeah, 1. Okay, this is D orbiter. So in the level of quantum number 2, 3, 4, and infinity, they will all have S, P, D, and F here. All of the subshell will be present, but whether they are occupied or not, if electrons, will depend on number of electrons in the element. Are you clear? All right. So from here, you can see here. Let's look at an example. So look at your periodic table. So let's look at Mr. Lee. Lee Hao-Ren.
Yeah, yes.
Hao-Yuan. Okay, give me one element. One element that you come in mind. Any element.
Oxygen.
Oxygen. Okay, let's look at O. Oh, okay. Everyone look at your periodic table. Oxygen number what? What's the atomic number for oxygen?
8.
8. 8 means what? 8 proton equals to 8 electron, right? So in your form 5, your teacher will tell you, okay, Murid, you write like this in this configuration. This is the way you write it. Yes, I know this is not correct. So 8 electron, you will write it how? It will be 2.6. Correct. And therefore, electron is placed where? Group 6. Because why? The valence electron is 6, correct? So you can see from here. So this is the way your teacher taught you 2.8.8 or 2.6 or 2. What? Does the teacher ever tell you 2.0? Never. Correct? 0 cannot be written there. It's always 2.8. Now, can you tell me 2.8? What element is this? Everyone? If I have the configuration of 2.8 here in your form 5, this is what? Neon. Neon is which group? Inert gas. Inert gas means what? Yes, group 8. Inert gas means the outermost electron valence must be 8, 8. So this is how you can refer to your periodic table and say, oh yeah, it's correct or it's true. But you can see from here, so this only comes to a limitation of knowing the electrons, but you cannot actually detect the presence of electron. So we want to find out how do we capture electron, because once you capture electrons, you can manipulate the bonding form from the electron here. Because formation of bonds come from the concept of what? Electrons. Sharing of electrons is what bond, everyone? Hello, everybody. When you have
Positive.
when you have
bond.
very good
Ionic
covalent
bond.
bond, good, fabulous. Okay, when you donate electrons, an element that donate electrons will become what? Having lesser electron, and therefore they have more proton, correct? So what you have here is a positive charge ion formation, correct? So what you have here, it becomes ionic bonding. If they donate, someone must take, someone is willing to give, there must be someone who is willing to accept. So therefore, this is give and take, give and accept. So this is ionic bonding. We talk about bonding later on. Are you clear? So what you have here, we're talking about oxygen. Mr. Lee given oxygen. So oxygen, can you see from here? So if we were to write SPDF configuration, all right, so let's look at the one that I have here. Can you see? This one is easier. Can see everyone? So you have this in mind. This is given to you in a supplementary in a Google Classroom here. So I told you that this is the way to remember the technique. So you don't have to memorize, oh my goodness, when I'm going to have a 2S coming before 3P or 4S coming before 4D or how. No, this is the technique. Are you clear? So the technique is number one, you have the arrow. You have the arrow here. Right, you have the arrow here. So basically, start from 1S. You see how I use my arrow, 2S. Then I come to 2P. Sorry, a bit tricky. 3S. Then you come to 3P. 4S. You see? 3D. 4P. 5S. You come to 4D. 5P. 6PS, and etc. etc. So in this way here, do you need to memorize anything? No. You just need to know how to write this down as a beginning point when you see a question on the electronic configuration. So my techniques I teach you now, you write 1, 2, 3, 4, 5, 6, 7 up to infinity. All right, you don't need to write all. So we know that all these are representing what, everyone? N, correct? Principal quantum number. So each principal quantum number, they must have what? The subshell, which is what? The S, P, D, and F here. So SPDF will be 1S. So I'm supposed to have a 1P here, but I won't write 1P because according to the formula of 2n power of 2, how many electrons can I take? Dual only when n equals to 1, correct? When n equals to 1 is only 2 electrons. So next one, we go to 2s, agree? So would it be a 2p? Yes. Would it be a 3d? Sorry, would it be a 2d? No, they won't be. I will need to write when it's not there. So don't do extra things when it's not needed, all right? So next one, when n equals to 3, do we have an S there? All right? Do we have a P there? Do we have a D there? All right, you follow the order. So you just need to write this down one by one. Then you will not get it wrong. You will sure score. I'm sorry, you will sure score if I ask you on electronic configuration. Definitely you will score. This is a technique. So when I teach, I'll show you technique. You don't need to crack your head. All right, so this is going to be 4P. This is going to be 4D. Now 4F possible. All right, and 5P and 5D and 5F here. So can you see? I already arranged it sequentially down. It's very simple arrangement. I'm sure you can remember that. So what you need to do next one, just follow the flow. Up, down, up, down, up, down, like you're cruising down a cliff, up and down, up and down. Then you will not forget the flow of the way to write electronic configuration. Is it clear? Is this clearer, class?
Yes.
Students? Okay. Is this better than the first time I saw you?
Yes.
Clearer, huh? So
True.
this is the only thing you need to know about electronic configuration. All right. So now going to orbital. So orbital means they are small boxes of the subshell. So in the S subshell is only one box. Why? Because it can only take how many electrons? Let's change color. Huh? How many electrons can it take?
2.
It's the rule. You must follow the rules here. It's a rule. It's not set by me. It's set by some physicists who discover. So the rule says that you can only fill in one electron. You always fill in electron. If this is this thing. Sorry. Let me erase this. Goodness. Okay. Now I just erase the whole thing. Just draw again. Patient. Okay. So we will have a P subshell. It will have 3 boxes. So each box of this, let's stick back to the same color. It will take in 1 electron at a time. The filling up must be done in this way. All right. Now can you see? I only use this way. Each of the arrow represent an electron. So this arrow means electron is having a positive spin. This arrow means electron is having a negative spin here. So some textbook they use this arrow. Also can. Both sides of the arrow. If you use partial arrow, it means the same thing. Either way is acceptable. All right. So you can see from here, basically, you fill up the electron based on the order of the electron here. You cannot fill in as anyhow you like here. There is a way to do that. So electrons are being filled up here. So can you tell me, if I have this electronic configuration, what element is this? Anyone? Can anyone tell me what element is this? Anybody? You can't. Why? Because you do not know whether it's filling up at 1s or 2s or 2p. Correct? So you must have something indicated to you here. So what you have here, this configuration of drawing the electronic configuration is not complete, because here it doesn't tell me which level of the quantum number I'm at here. So basically, I miss out one here. What should this box be? Anyone? This should be what? This should be 1s. This should be 2s. This should be 2p. This should be, is there a 2d there? No, there's no 2d. So let's erase this. All right. The next level that you go to should be what?
3s.
Yes, very good. How many boxes there?
5.
1.
S is one now, friend. One box there.
1.
One now. So we have what? Next one is what? 3?
3.
Three. How many boxes there?
3 boxes.
3.
Good. All right. So if I tell you, all right, I have the two blue electrons. Each arrow represents one electron, correct? Two blue electrons here. All right. So I have 1, 2, 3, 4, 5. I have 5 electrons here. What element is this?
Argon.
No. I do not know, because I didn't fill up here. So this is the wrong way to write the configuration here. So I must always fill up from here. If I want to have 1 electron, 2 electron, right? 3 electron, 4 electron, 5 electrons, 6 electrons, 7 electron. So how many electrons altogether here? 7. 7 electron refers to which element? Look at periodic table.
Nitrogen.
Nitrogen. Very good. So nitrogen is 7, 14, this is the chemical symbol, So can you see from here? So if I want to draw an orbital diagram, this is called orbital diagram here. You don't need to know at your level. You need to know only how to write electronic configuration. So basically, these boxes here, you don't need to indicate in your level. All right, this is for chemistry people. All right. So what you have here, if I want to write nitrogen, electronic configuration for nitrogen, what should I do? I should write 1s2, 2s2, 2p, 3. Agree? Because it can only take 3, It doesn't need to take all the 6, It fill only up to 3. So this is your electronic configuration for what? Nitrogen. Anyone lost? So your question to me, you may ask me, Miss Ng, why do I fill 1, 1, 1? Why can't I don't like to fill up in this way here. Can I do it this way? Can I do it this way? Yeah. Can I do it? Can I fill up my electron in this way? 1, 2, 3. I'm still filling up 7 electrons, but the technique that I fill up here is not correct, because there's a rule to follow. You must always fill up electron in the same direction of spin. Then only you can apply it to the right configuration. So you cannot have can I fill up in this way? Let's check out. Let's do it. Can I fill up in this way? Can I do it this way? Can I? You can't. So you must always fill up the electron. One arrow indicate electron in the order of the spin. Up, up, up. Then if you go on to the next one, if you have one more electron here, now you tell me what element is this? 2, 4, 6, 8. Oxygen. Am I right? Is this oxygen?
Yes.
If I have this configuration, it's a 1s2, 2s2, 2p, 4. All right. So oxygen. This is the electronic configuration. So can you tell me what's the valence electron for oxygen?
6.
6. Why 6? Because it's in group 6, that's why it has 6 valence electron. I think you know that. So where do I get 6? You see? Now I look at the outermost quantum number, which is what? Outermost quantum number for oxygen is what? Number 2 ma, 2. It's still at number 2 ma, n equals to 2 ma. So at n equals to 2, how many electrons does it have? 2 plus 4, 6. Follow me? That's why you get the valence electron. That's why in your form 5, if you were to do this, the way your teacher taught you is not wrong, it's right at that level at the time. But if you go higher level, you have to know that this is better to explain why does some behavior for some metals, for some materials here, they can transfer energy, and then some can conduct electricity, and then some can have good thermal conductivity. So this all comes from where? Electronic configuration. So if you were to stay in this way of writing electronic configuration, absolutely there's nothing wrong here, but then you cannot explain the phenomenon observed by the character of a certain material here. And therefore, especially when it comes to semiconductors material, all right, the energy band cannot illustrate clearly by this way of writing electronic configuration. Any questions from anyone here?
Miss, I have a question.
Yes.
What is the purpose of for indicating the electron spin direction?
Oh, the electron spin. Let's look at here. This is the one I'm talking about, electron spin just now. So electron spin means if you can change the spin, it means you can change from, let's say, I'm talking about iron being a paramagnetic, it becomes ferromagnetic, it becomes ferrimagnetic. We know all iron can be magnetized, correct? Agree? So
Agree.
all iron-based material, they can be magnetized here. But then, can I make my copper? Can I make my nickel become magnetic? I can't. Why? Because of the spin there. Are you clear? Of course,
Yes.
within the spin here is more than that here. It's not just the spin here. The spin must be done in certain manner, certain orientation here. So the special thing about iron here, that's why iron is the most abundant mineral in the world. All right, iron is the most stable mineral in the world as well. That's why everywhere you go, you see iron, rather than the rare earth or the rare earth metals or the what so-called precious metal like the gold and the platinum and the silver here. Iron is quite easily mined in anywhere that you go here. Probably you have iron behind your home as well here. All right, very good question. Thank you for asking. Ask me question. Anything else here? Anyone?
Miss, I saw
Yes.
there it says the spin you can indicate by positive 1/2 and negative 1/2. The 1/2, does it indicate anything?
Yeah, it is the magnitude of the spin here is half. It's not 1/2. It's half positive, half negative here. That's why you see add up together. You see I draw half. All right. So can I draw it as full arrow? So can here. So the spin refers to clockwise, anti-clockwise, upward, downward. So the spin is very important. The spin is the one where you design it for smart materials. And of course, together with that, magnetic quantum number is the one that when you subject a certain element onto magnetic field, how does it react? Because nowadays we have all the nanomaterials. Those nanomaterials, they are very, very delicate, especially your smartphone nowadays. You can see the heating problem is one of the problems that need to be solved here. The heat that is being transmitted, the heat that's being dissipated, it is always an issue for all semiconductors and advanced materials. Follow me? Can?
Yes, thank you, Miss.
Can I go on? So let's look at here. So by now, this is the electronic configuration. We know that we start from a principal quantum number n of 1, 2, 3. Then after that, we know that lowest of it always start from 1. It has the lowest energy. The highest will go to infinity. And we know that each of the shell, based on the quantum number, can fill up certain number of electrons. It cannot go beyond that. There's a ruling to that here. All right, and with this in mind, the subshell is indicated by SPDF. Each of the subshell here, also we will align them according to the energy content. So can you see the importance of knowing the energy in the electron? So if I know the presence of energy, I can measure, all right, then I can know electrons are there. So if you know electrons are there in that region of space here, you can manipulate the behavior of the electrons, and therefore you can form new materials, more advanced materials. That's why they have smart materials here. All right. So all right. So this is again arrangement of electron based on energy content. All right. So let's go on to the one that I want to talk here. So again, you're expected to know how to write electronic configuration. So this is 1s2, 2s2, 2p6. So how do I know what element is this? Look at the superscript. Raymond, all right, look at the superscript at the top there. Add up together all the number. How many here? 2 plus 2 plus 2. 2 plus 2 plus 2
10.
plus 2 plus
10.
6 is 10. 10 is number what? Element number what? Neon. So you must make sure you know that if I look at the superscript here, all right, that they indicate the number of electrons of the element. Don't not add the 1 and the 2 and the 2 here become 5. No, this represent what? Quantum number, which is the level of where the electron is being placed. All right. So filling up of electron is in this order. This one up from 1s to 4p. So can you see the order is not always in the right way because of the energy content of the orbital. As you go higher energy principal quantum number here, it becomes more complicated. All right. So let's recap. So electronic configuration, hydrogen is 1s1, helium is 1s2. That's why you see is helium in group 2. Check your periodic table. No, helium is not in group 2. You know why? Our friend, the hydrogen and helium are special, very special, because they are super light element here. So helium is in where? Helium is in group 8.
18.
But
Group 18.
yeah, 18. 18 is group 8. But helium is actually an inert gas. Inert gas for noble gas, which is the group 8. If you look at the group 8, group 8, all right, group 8 is inert. That means it is going to be 2. If you write the normal configuration in your form 5 is 2, All right. So what you have here basically, is this fill up? The keyword is this fill up? Yes, it's fill up. It's fill up. So is this stable?
Yes.
Yes.
Yes, it's very stable. So can you remove electron from here? You
No.
can.
Cannot.
You can.
Oh,
But very hard. You can. You sure can. You have to have a lot of energy. Where does the energy come from? External energy. You bombard helium with what?
heat energy.
Bombard helium with what? Gamma ray. Okay, then you get ionized helium charge at charges here. So you can remove this electron, but you need a lot of energy, tremendous energy. But compared to my friend here, this is lithium. Lithium outermost valence electron is 1, correct? So this is why my lithium is in group 1. So can I easily remove this electron?
Yes.
Yes.
You can. Remember, now there's a keyword here. This is called partial filling. Because the s orbital can take 2, but my friend here, lithium, has 1. So it is a partially filled configuration. So a partially filled configuration is also quite stable. So therefore, not easily to remove them, but you still can remove them. You need energy. Follow? All
Sure,
electrons
but-
can be removed. Yes.
But I thought the like lithium, right? And the one, the 2s1, it's on the outermost shell of the valence electron.
Yes, it's on the outermost shell of the it's the outermost from the nucleus attraction. So this is also the outermost shell, correct? All right. So this electron is the outermost as well here, but remember, lithium is very small. The size of the atom is very small. So the pooling of the nucleus for these 3 electrons is very strong because there's no shielding. We call it shield. You do not shield away the electron from the nucleus attraction. We have the shielding effect. Can you follow me? Shield. Shield means you protect it away. Like you have a bulletproof casing there. So same thing over here. All right. Did I answer your question? Can?
Yes.
All right. You can still take away the 1. All right. That's why lithium is what? Group 1. Group 1 means what? It will form a positive charge ion. All right. So next one. Let's look at here. What symbol is this? What element is this? Sulfur. Sulfur has how many electrons? 2, 2, 6, 10, plus 2 and 4, 16. Check out your periodic table. Is it 16?
Yes.
All right. So what group is sulfur in? You tell me.
Group 16.
Group 6. How do I know 6? What is the outermost quantum number? 3.
3.
3.
All right. So the number of electrons in here, 2 plus 4, 6. That's why you can explain why should I put my sulfur together with oxygen, because they have the same valence number of electrons. All right. Clearer? Can? So this is to tell you. All right. The arrangement of the periodic table is beautiful, really beautiful in a way that you can explain. Now, only in the shell level, sorry, only in the S level here, you can find the group 1 and 2. Only in the P level, you can find the group 3 and 8, and the lanthanides and the transition element are in the D and F here. That's why you see transition element are very complicated element here. You know they have a very high what oxidation number, and they have a lot of what color. Remember your copper? Copper can be green, can be what color is copper? Can you remember in your form 5, your chemistry?
Blue and green.
Yeah,
Cu2 positive blue.
same. Yes, it has many colors here. That's why it's transition element here. They are very complicated. The electrons are being placed higher level. D comes in here. Therefore, there are more ability to play with the electron to allow the electron to move from one orbital to the next orbital. It can be done. All right. So let's check. Up this slide is okay. Is it all right? This slide. Any questions so far? If you have gone through, no. So I want to go to did I do this? Where did I stop? Have I done this?
Yes.
I've done this.
Yeah.
True, really. Okay, I've done this. Mr. Ngu, have I done this?
Yes.
Yes, sir. All right. So, all right. So let's look at here. Yeah, I've done this. Now, coming to this part here, you see orbital. Orbital means what? The small boxes there. So in the P subshell, you tell me now how many boxes are there?
3.
3. All right. In the D subshell, how many boxes are there? 5. All right. How many electrons are there in the 3D subshell? D subshell? I don't care whether it's 3D, 4D, 5D. 10 electrons there.
10.
Space. Yes. All right. So now the arrangement of electrons, you can see the energy come in from 1s, it goes all the way up to 4D and for etc. So you can see between 4s and 3D, it jumps. All right. There's a ruling to that. This is called off birth. It's time, sir. So I don't want to hold your time here. Let me go to here. I'm not skipping any slide here. I just want you to go back and read through this. You see this? Off birth. Where is that? Off birth. Off birth is a physicist here, very smart guy there. All right. So he says to you that this one will give you deviation. It's not always that you follow the order of how you arrange the electronic configuration based on energy level. So in certain extent here, they don't follow. And therefore, you have this, remember, this is the 8. And you can explain to me why is it that the 3D comes after the 4S and not before the 4S here? And why does the 5S come before the 4D? All right, so this is the explanation behind it. So I shall have to stop here. Can I recap? Guys, this will be the last page that I stop here. Where is it? All right, this is the last page that I will stop here. Is that clear? Is it okay?
Okay.
Yes.
Yes.
Okay, the also I stop here, correct? So okay, record down. Slide 39. Okay, so I'll see you again on Tuesday. The Monday group, I'll see you for lab. So read through the lab manual, look at some of the reading, and then we will discuss on the crystal structure on Monday. Thank you. Have a wonderful yes.
Miss, I want to ask you for the
Yes.
de Broglie wavelength. What is the H?
Come again. Repeat your question again. Sorry.
For the de
De Broglie.
Broglie wavelength, there is a formula below it, and I would
Yeah.
like to ask what is the H because it's not stated.
Planck constant.
Okay. Now the Broglie wavelength. All right. It simply tells you. I'm sorry, I overshoot the time. All right. Electron behave like a particle. At the same time, it is a wave here. So when you have a wave here, lambda comes in. Lambda is wavelength. All right. H is Planck's constant. All right. Planck's constant comes from the concept that if I have a certain wavelength, it can also give me a certain frequency. So this Planck's constant is actually equal to finding of the energy of the radiation is equal to HF. All right. So the relationship of the energy content of a radiation is proportional to the frequency of the wave that is exhibited. And this must be obeyed by a constant. This is called the Planck's constant. Let me spell it out for you. Planck's constant. Planck's. Okay, so Planck's constant is very important because one thing I want to highlight to you, you know electrons are wave. Wave are electrons. So what kind of wave are we talking about here? Electromagnetic wave. So if you find that your electromagnetic wave, we have we have the gamma ray, microwave, visible light, UV. All right, we have the IR. All these are actually electrons. They are electrons here. So electrons are wave. Electrons are wave. Wave are also electrons here. So these members of the electromagnetic wave all belongs to radiation. So the discovery of electron brings about to the finding of radiation here. So the radiation that you have known in your life here is probably X-ray or gamma ray. Right? In fact, these are all members of what? Electromagnetic spectrum. All right. So now let's look at this formula. M is what? M is mass, ma. So why is mass coming in here? Can you tell me? Because electron behave as a particle. So if it's a particle here, it will have what? Mass. Even though it's very minute, you can't see by naked eye. It has a mass there. It's very, very small. It's actually close to zero there. So what you have here, electron is also at the same time moving, it's spinning. It's never stationary. It's always spinning around, revolving around the nucleus. So this is the formula from the Broglie wavelength here. So in explaining why does the electron behave as a wave, at the same time it is explained as a particle, this formula applies. That means I can have a wave function of lambda wavelength in knowing that it has a mass, so I can predict how fast the motion of the electron here. All right. I hope this explained to you.
Thank you,
Now,
Miss.
in the exam here, this will not be asked here, don't worry. Because this the Broglie wavelength here together, if you read online, you have to know Schrodinger equation. Schrodinger equation. All right, and of course, there are a lot of calculus behind it because they are deriving the findings of electrons to predict quantum mechanics here. All right, thank you for your question, Mr. So. Any more?
Okay.
Anyone?
Thank you,
About
Miss.
the attendance.
Yeah.
Attendance. How?
I don't know, you should be quicker now. Wait, this is another hiccup there. I'll get to it here. Wait, let me screenshot everyone. Wait, hang on there, hang on. I can screenshot everyone. Wait, this is all captured on be recorded, so I'm going to scroll this down. So everyone's name should be here. There are 33 of you, including me should be 34, right? Someone left? We shall look into that. Anyone left? So this is captured, so I can actually have this in my video as well here. Is it all right, everyone?
Yes, Miss.
Okay. So thank you for your patience. Thank you so much there. And I'm sorry I overshoot the time 7 minutes. So I'll continue next Tuesday again.
Sure. Bye.
Okay. Have a nice evening. Bye bye.
Thank you, Miss.
Thank you, Miss.
Okay, thank you, Miss.
Thank you, Miss.
Thank you, Miss.
Bye bye.
Thank you, Miss.